All right, this is the Unit 1 review for Math 3. Number 1, we're asked to graph an equation. First, notice that that equation is squared, and so we're going to be graphing a parabola here. Also, we have the x minus 4 inside of the parentheses. The number with the x translates the parent graph left to right. In this case, that minus 4 is going to move us to the right 4 units. And that plus 2 tagged on at the end is going to move us up 2 units. So we can get our first point by knowing the parent graph of a quadratic has a point at 0, 0. If we take that point from 0, 0, move it right 4 up 2, we get a point on our new graph. So from 0, 0, move right 1, 2, 3, 4, up 2, and there's a point from our graph. We know that this graph is opening down because there's a negative out in front. That leading coefficient is negative, but we need some more points. In fact, it's good to come up with at least 3 points to graph this. And so I'm going to plug in another value. We have a value when x is 4, so let's plug in 5 for x and see what we get for y. So when x is 5, we end up with y is negative 2 times 5 minus 4 squared plus 2. 5 minus 4 is 1, and 1 squared is still 1. So we end up with negative 2 plus 2, which is 0. So when x is 5, 0 is our y value. Because the first point is our vertex and we have symmetry in our graph, we get a third point automatically. And so here's a sketch of the graph we're working with. All right, number 2. We have another equation that we're going to graph. Here we have the absolute value sign, so this is going to look like a V shape. Again, the parent graph of the absolute value has a vertex at 0, 0. This is a translation of that. So that plus 3 inside the absolute value is going to translate us left 3, or translate the parent graph left 3. And that minus 4 tagged on at the end is going to translate the parent graph down 4. So from 0, 0, I'm going to move left 3 down 4 to get my first point. Again, we need some more points here. The leading coefficient is positive, so this is opening up. Because this is a linear absolute value, we get that a V is created by 2 line segments. We can use that 1/2 and think of that 1/2 as a slope to help us find another point. Remember, slope is rise over run, and this is really the slope of the right half of our absolute value only, okay? So slope of right half. So from our point, we can go up 1, right 2. And then because this is symmetric, we can go up 1, left 2 to get a third point. And there's our graph. Number 3, we have an exponential function. All parent graphs of exponential functions pass through the point not 0, 0, but 0, 1. And so we're going to translate the parent graph. In this case, that x plus 2, the 2 is up in the exponent with the x value, so that's going to move us to the left 2 units, or translate left 2 units. But here, be careful, we're not translating from 0, 0, we're translating the point 0, 1. So if we start at 0, 1, move left 2 units, we're at negative 2, 1. The parent graph has a horizontal asymptote along the x-axis here. And because we have not translated the parent graph vertically, it's still there. So let's label that y equals 0. And then let's get a couple more points. If I plug in, let's say negative 1, which is 1 point right to negative 2, because we have the value at negative 2. So I'm just going one value to the right. We end up with 3 to the power of 1, which is 3. So when x is negative 1, y is 3, I could plot that point. And let's get another value. If I plug in 0, which is another, just moving to the right one more unit, we get 3 to the power of 0 plus 2, or 3 squared, which is 9. So 0, 9 is a third point. And we're a bit off the graph there. So remember, on the left-hand side, the graph approaches our horizontal asymptote, never crosses it, never even touches it. So we get something like that. And there's g of x. Number 4, again we have an exponential function, and if you compare it to number 3, they almost look exactly the same. The difference is where the plus 2 is. In example 3, the plus 2 is part of the exponent. In example 4, that plus 2 is not part of the exponent. So here our translation is we're going to translate the parent graph up 2 units instead of left 2 units like we did in the previous. But remember, because it's exponential, we're translating from the point 0, 1, not 0, 0. So up 2 units from 0, 1, we end up at 0, 3. And then we need a couple extra values. So I have a value for x, so we already have 0, 3. So let's plug in 1 for x and see what we end up with. And we end up with 5. Oops. So 1, 5. And if we plug in 2, we end up with 11, which is off our chart here, somewhere up here. One more thing we need to graph before we draw our curve through those points is the horizontal asymptote. The parent graph normally has the horizontal asymptote at the x-axis or at y equals 0, but everything has been translated up 2 units. So now our horizontal asymptote is right here at y equals 2. And so this curve goes through our 3 points, approaches horizontal asymptote to the left, never touches it. Number 5, we have a piecewise function. F of x is equal to negative 5 only when x is less than or equal to negative 3. And f of x is equal to 2x minus 3 when x is greater than negative 3. And so when we're evaluating our function, we need to know which of the two functions we're working with. So our first one, f of negative 5. X is negative 5, and so negative 5, well, how does that compare to negative 3? Negative 5 is less than negative 3, and so we are going to be working with the top part only, and so we can write f of negative 5 equals, our answer is negative 5. On the second one, we want to find f of negative 3. Here x is negative 3. That's not greater than or less than negative 3. That's actually equal to negative 3. So again, we're using that top line there. And we end up with f of negative 3 is equal to, again, negative 5. Third case, f of 0. X is 0. 0 is less than, actually, 0 is greater than negative 3. And so we are using the second line in our piecewise function. So f of 0, in this case we plug in 0 into 2x minus 3. And we get negative 3 as an answer. And lastly, f of 1. Again, when x is 1, that's greater than negative 3. We're using the second line again. So plug 1 into 2x minus 3, and we end up with 5. Number 6, we're given a graph of a function, and we want to graph a transformation of that function. So on part A, what does it mean to have that x minus 4 in parentheses? That's telling us to move to the right 4 units. So everything in the graph of g of x, we're going to move to the right 4 units. So go point by point. The bottom left-hand point looks like it's at 1, 2, 3, 4, negative 5, negative 3. So start there and go right 4 units. And that's where that first point is. In that line segment that I'm circling here, that the right end point, which is open, is at negative 2, 1. So start at negative 2, 1 and go right 4 units. Put an open circle, make sure you match it, and connect those points. So that's that first part. You can also look at the relationship between the points. For example, since I have that first part drawn, I can say, well, how do I get from that open circle to that next point? And if I go right 2, up 1, I get to that next point. And I could just do that, right 2, up 1. And I can do this again. How do I go? I'm going to go down 1, 2, 3, 4, 5, right 2. So down 1, 2, 3, 4, 5, right 2. Draw a little curve. And then from that point I'm going up to right 2. Draw a little curve. And then I've got my graph. Alright. For part B, we are going to do something similar. We need to know what that minus 4 tagged on at the end. It almost matches A, but that minus 4 is not in the parentheses with x. So when it's on the outside, tagged on at the end, that's going to translate everything down 4 units. So again, we pick a point on the original g of x and go from that point. Here I'll start maybe from the center. So that's an easy point to start at. We have one at 0, 2. And I'm going to, so from 0, 2, drop down 4. And there I have it. Just keep track of what point you're working with. And then if I want to move left, I want to go from that point to the open circle. I'm going to go drop down 1, left 2. Open circle, don't connect them because they're not connected in the graph. From the open circle to the closed circle, moving left, I'm going to go down 1, 2, 3, 4, and left 3. Closed circle, connect those because they're connected in the graph with a line segment. And then I'm going to move to the right from the center. So I'm going to drop down 1, 2, 3, 4, 5, right 2. And then up to right 2, and draw a curve through those points. And so if you compare the original with part B, it should look like a translation down 4 units. See, we have a negative sign in front of g of x. That is a reflection across the x-axis. So we go back to our original graph here, find a point, and reflect it across the x-axis. So if it's above the x-axis 1 unit, we're going to go below the x-axis 1 unit. Or if it's above the x-axis 2 units, we're going to go below the x-axis 2 units. So we have this one right here is 3 units below, this one's 1 unit above, 2 units above, 3 units below, 1 unit below. And so when we sketch ours at -5, when x is -5, we're going to go 3 units above, solid. When x is -2, we're going to go down 1 unit, open circle, connect them. When x is 0, we're going to go down 2 units, close circle. Going back here, when x is 2, we're going to go up 3 units. And then when x is 4, we're going to go up 1 unit and draw a curve through those 3 points. And then lastly, part D, again, compare C and D. In C, the negative sign's out in front. That's when you reflect about the x-axis. On D, the negative sign is in the parentheses in front of the x. That's when you reflect about the y-axis. So you want to go back to the original function, and this time you're going to look at how far each of those points are, not from the x-axis, but from the y-axis. If a point's on the y-axis, it stays on the y-axis. This point right here is 2 units to the right, so we're going to move it 2 units to the left. This one right here is 4 units to the right, so we'll move it 4 units to the left. Same height. The height doesn't change. This is 2 units here. This one is 5 units. So let's work through this. So when when y is 2, that height of 2, that's going to stay there. Okay. Moving down, when y is at 1, we're going to, instead of going left 2, we're going to go right 2, and it's an open circle. They're not connected. Moving down, we're at a height of -1. Instead of moving right 4, we're going to move left 4. Close circle. and then move all the way down to a height of -3, and we're going to go left 2 and right 5 from there. These two connect, U-shape through those points, or J-shape. And there we have it. Number 7, we're given another a graph of a piecewise function. And part A, we're asked over which interval do you see a quadratic function? So a quadratic function is more of a U-shape. I'd say I'll highlight it, thinking maybe that would be our quadratic function. We have an exponential function, just looking at the shape, not doing much other than that to verify. A linear function, I'm going to use this for my linear function, and a linear absolute value function. You're right here. Now the questions A through B ask over which interval do you see these functions. It really should read which open interval, and that's what you're going to see on the test. And so we're going to answer these as just open intervals only. So over which open interval do we see that quadratic function? Well, when you interpret this, you're only looking at the domain, only the x values. So it's starting at the x value at -2. The yellow moves to the right all the way until we get to +2. And so open, -2, +2. That's interval notation. If we put it in inequality notation, it would look like this: -2 less than x, which is less than 2. On part B, our exponential function, on the x-axis, it looks like it's starting here at 4, and then it's got an arrow to the right. The graph, when we drew it, it stopped somewhere, at 6 point something, but that arrow means it's going forever in that direction. So from 4 to infinity, okay, or everything bigger than 4. So all x values greater than 4. A linear function, we have -2's the right endpoint, and -6 is the left endpoint. When you write your interval notation, always go left to right, so -6 to -2. If we put that in inequality notation, -6 less than x, which is less than -2, or everything in between -6 and -2. And lastly, the linear absolute value function goes from 2 to 4. And we can write it in either form. Number 8. Given the graph of g of x below, answer the following. So what's the domain of this function? So looking at the x, the lowest x value is at -1, 2, 3, 4, 5, 6, -6. The largest x value is over to the right at, it's not included, but it goes all the way up to 1, 2, 3, 4, 5, 6, 7. And so we include the left end point. We do not include the right end point. That's in interval notation. If we put this in inequality notation, it's -6 less than or equal. We include it, which is less than 7. Our range, now we're looking for the lowest and the highest point. The lowest point represented is at -2 on the y-axis. We do have an open circle at -2, but we also have closed circles, so as long as it's represented somewhere on the graph, it works out. And the highest point is at 4. So go lowest to highest, include the -2, include the 4. This is, we're talking about height, so use y. And there we have it. Part C, a bit more complicated. We got to write out a 4-piecewise defined function that accurately represents the graph of f, shown above using at least one of each of the following types of functions: linear, quadratic, and absolute value. So we need 4 pieces, and we have to use at least one of the 3 pieces. So for linear, we have a horizontal line that we can use. I'm going to use this as well as for linear. So there's 2 of my pieces. For quadratic, you can see it here. It's that U shape. And for absolute value, that upside down V shape. So that we see, I've highlighted the 4 pieces. We're going to go one at a time. So my first piece on the top left, we'll go from left to right, is the line y equals, well, what's the height? The height is 2, so y equals 2. So there's my first piece. My second piece is quadratic. I'll use green. Not only is it quadratic, we see the vertex is at -2. So the parent graph of a parabola has a vertex at 0, 0. So this thing has been translated down 2 units. So I know it's in this form: y equals, not sure yet, so I'm going to put in a, x plus 0 squared, because it hasn't been translated left or right, but then -2, because it's been moved down or translated down 2 units. So that's how the vertex came in play, helped us write out this much of it. Let's find another point on this graph. I'll use the right endpoint, which is at 1, 2, up 2, so 2, 2. Another point that it goes through. And I'm going to plug that in for x and y to help me find out what a is. To solve, I'm going to add 2 to both sides of the equation, and I'm going to square the 2 here, divide by 4, a is 1. So plugging 1 back into the original that I had here, we can finish this up as y is 1, which I'm not going to write the 1, x squared minus 2. So now we have our second piece. Third piece is another line. And I'm going to start at the left endpoint, the 2, 2. We know that the parent graph goes through the 0, 0. So this thing has been moved to the right 2 units and up 2 units. So y equals some slope, and we'll figure that out in a second. But it's been moved right 2 units and up 2 units. And then we can look and see, well, how do I get from the left endpoint to the right endpoint? You know, what's the rise, what's the run? It's dropping, so it's going to be a negative slope. So my slope is a negative. and then it drops 1, 2, 3, 4, right 1. So negative 4 over 1, or just negative 4. And so now we have our equation y equals negative 4, quantity x minus 2 plus 2. We can simplify that further. I'm okay if you leave it like that. And then lastly, I'll use blue. Notice the location of the vertex. The vertex is at 1, 2, 3, 4, 5, negative 1. The vertex of the parent graph is at 0, 0. So this has been shifted to the right 5 and down 1. So I'm going to start by y equals some number, which is the slope of the right-hand side, absolute value, been moved right 5, so x minus 5 inside the absolute value, moved down 1, so minus 1 tagged on at the end. Then to find a, I'm going to look at the slope of the right-hand side. So from the vertex to the right endpoint, I drop down 1, right 2. And it's a negative slope, so negative 1/2. So y equals negative 1/2, absolute value of x minus 5 minus 1. So now I have my 4 different pieces, but all 4 of these pieces belong to a function over some interval. Okay, so that first equation, the y equals 2, it's only y equals 2 from certain x value to another certain x value. You know, the left-hand side, the furthest left we go is 1, 2, 3, 4, 5, so at negative 6. And the furthest to the right we end up as at negative 2. So this is true only for x between negative 6 and negative 2. And we want to include the endpoints because the dots are filled in. For the second part of this piecewise function, the left endpoint's at negative 2, the right endpoint's at positive 2. That's how far right that goes in green. And so that's true only for x between negative 2 and positive 2. Make sure you include them again because we have a closed point at each endpoint. The third part, the line, highlighted in yellow, the left endpoint starts at an x value of 2, the right endpoint an x value of 3. So that's only true for everything between 2 and 3, when x is between 2 and 3. And then our absolute value is true from 3 all the way over to 7, but 7 we don't include. So that's true for x between 3 and 7. Now, we need to adjust some of this because we've been handling these pieces separately, and when we put them together, we can't have the same point belong to 2 functions. So we need to adjust something really quickly here. And so let me point out what I mean. That point I circled in red. We need to decide, do we want that point to belong to the line, or do we want that point to belong to the parabola? We cannot, when we put everything together in our piecewise function, we can't have it belonging to both. And so it does not matter which one belongs to which. I'm going to make it belong to the line. So I'm going to leave the line alone. But if that point belongs to the line, now I have to change that sign. that less than or equal sign to just less than, because when x is 2, it's going to belong to the line, not to the quadratic. So the domain is now -2 less than x less than or equal to 2. And then if we take a look at the next shared point, which is when x is 2, we have to again decide, does that belong to the parabola or to that line that we highlighted in yellow? We need to make a decision either way. I'll make it belong to the parabola. It won't belong to the line. So again, I'm going to have to change that less than or equal sign to a less than sign. And so we get 2 is less than x, less than or equal to 3. I'm going to scratch out the old ones here. And then we have that issue one more time at the 3. I'm going to let the point at 3, -2 belong to the line, not the absolute value. So I'm going to change that to 3 less than x, less than 7. And now we have the 4 equations with domains that worked well together. So let's take those 4 pieces, put them together in one function, and that's what we call our piecewise function. So here's our function f equals, our first piece is y equals 2. If -6 is less than or equal to x, which is less than or equal to -2. Our second piece is y equals x squared, and we don't really write the y equals, so I'm going to go back and get rid of that y equals 2 because it's really y is f of x, so it's f of x equals 2 if x is within that range. So the next one, y equals x squared minus 2, so I'm going to just write x squared minus 2, and that's if -2 is less than x, which is less than or equal to 2. The third piece, y is -4 times x minus 2 plus 2. If 2 is less than x, which is less than or equal to 3. And then the last piece, y is equal to -1/2, absolute value of x minus 5 minus 1 if x is greater than 3 but less than 7. That is our answer. A lot of work involved there. Take your time, make sure you have the right equation, and then after the right equation, the right domain for each equation. And just remember, the different pieces cannot share any points. Number 9. We have an exponential function that we want to sketch with at least 3 lattice points. A lattice point is a point that goes, it has an integer x coordinate and an integer y coordinate. So it's going to go where you have those little lines crossing. And then we also want to identify the domain and range. So the parent graph of all exponential functions go through the point 0, 1. This particular function, f of x, has been translated left 1 and down 3. And remember, this is from the point of the parent graph at 0, 1. That's the y-intercept of the parent graph. So from 0, 1, I'm going to go down 1. Sorry, I'm going to go left 1, down 1, 2, 3. The parent graph also has a horizontal asymptote at the x-axis. Everything's been translated down 3 units, so now the horizontal asymptote is the line y equals -3. And then we want a couple other points. So we have one lattice point right now. We need a couple others. So I have the point when x is -1. I'm going to go 1 to the right, plug in 0, find f of 0. And we get -1 as an answer. So 0, -1 is a lattice point. And then I'm going to plug in a 1 for x. And we get a 1 for y. So 1, 1 is another lattice point. And so as we move to the left, our graph approaches that horizontal asymptote. It never touches, it just gets closer and closer to it. We have our 3 lattice points, and there's our graph. Number 10, we want to sketch the absolute value equation. Remember, that looks like a V. The parent graph has a vertex or y-intercept at 0, 0, but this has been translated up 3 units from that. So I'm going to move from 0, 0 up 1 to 3 units. I have my first lattice point. Also, this is an absolute value. It's a linear function, but it's an absolute value linear function. So we can use the idea of a slope. If we look at that -2/3, that's the slope of the right side of our V. And so it's negative. And so from our vertex, I'm going to drop 2 units and go right 3 units. That's the -2/3. And this is symmetric about our y-axis in this case, because that's where our vertex is. And so I'm going to drop 2 units and go left 3 units to find a third lattice point. And we have our graph. Number 11, we want to accurately graph using at least 3 points and label both f of x and g of x, both absolute value functions, on the same coordinate axes, and then describe the transformation in words from f of x to g of x. So I'm going to plot f of x in blue. Notice f of x is a parent graph. Goes through the point 0, 0. If you plug a 0 in for x, you get a 0 for y. It's got a slope of 2. So if or if you could just plug in a point as well. If you plug in 1 for x, you're going to get 2 for y. If you plug in -1 for x, you're going to get 2 for y. So however you want to come up with those points, I'm going to use the slope. So think of it as a fraction. Rise over run, up 2, right 1. To get my second lattice point, up to left 1, because of symmetry, to get my third lattice point. So that's f. G I'm going to do in the color green. G has been translated to the left 3 units and down 4 units. And we've already graphed or plotted this parent graph. And so you could take those 3 lattice points that we already plotted, move them left 3 down 4. And we have our sketch of g of x. Describe the transformation in words from f to g. So G, our result, is a translation three units left. and 4 units down. From the parent graph f of x. Number 12. Accurately graph using at least 3 points and label both f of x equals negative 1/3 x squared and g of x equals negative 1/3 x plus 3 squared plus 4 on the same coordinate axes. Again, notice f is a parent graph, g is a translation of that parent graph. Describe the transformation of words from f of x to g of x again. So again, starting with the parent graph. It's a parabola, we know that because we have the x squared. It goes through its vertex is at 0, 0, or its y-intercept is at 0, 0. You can confirm that by plugging in 0 for x and solving a unit for y, and you get a 0 for y as well. And then we can plug in 1 unit to the right of our vertex to get another point. But notice when we do that, we end up with a fraction, negative 1/3, which we can graph. It doesn't say at least a lattice point, but it's a little easier to graph a whole number. So we need to be careful what we want to choose to plug in for y. It has to be divisible by, for x, it has to be divisible by 3. So let's plug in 3. So we get negative 1/3 times 3 squared, which is negative 1/3 times 9, which is negative 3. So if I go right, so 3 negative 3, and that's the right hand side, and because of symmetry we're going to have something at negative 3, 3 as well. Negative 3, negative 3. Now g of x is just a translation of f of x. And we're going to go left 3 units, and we're going to go up 4 units. And since we already have f plotted, we can take those 3 lattice points and move them left 3 units and up 4 units. And we have a sketch of g of x. So g of x is a translation (3 units left) and 4 units up from f of x. We're given a piecewise function. Actually, sorry, you know what? Did I do everything that was asked? Going back, sorry guys. Number 9 and 10, I did not fully answer those. It says to identify the domain and range as well. Let me do that real quick here. So going back to 9, we have it sketched. The domain is, how far left is this graph going to go? How far right is this going to go? And the arrow is pointed to the left. That means it's going all the way to negative infinity. The right side is pointed up and to the right, so it's going to go all the way to the right to positive infinity. So for our domain, it goes from negative infinity all the way to positive infinity. Or we can say all real numbers. for the range, what's the lowest point represented on this graph? Well, it gets really close to a y value of -3. Never gets there, so y equals -3 is, in a sense, a boundary. It's never going to be equal to it, but it will get as close as we want to it. What's the highest point? It's going to go as high as we want, and so lowest point, -3, don't include it. Highest point, as high as we want. Or how do we say, how can we write an inequality, everything bigger than -3? We're talking y values. Y is greater than -3. On 10, we also wanted to state the domain and range. Sorry, I forgot to do that. The domain on 10, how far left, how far right. Again, we have arrows on the left pointing down, but to the left, as far left as we want to go, so -infinity. And the right side is pointing down and to the right, so it's going to go as far right as we want. So from -infinity to +infinity. Or again, we can say all real numbers. For our range, it's got a highest point. It's not going to go any higher than 3, but there is no lowest point. Both arrows are pointing down, and it goes as low as we want. So the lowest, well, is -infinity. The highest is 3, and that's actually included. So we can also write that as all y values less than or equal to 3. And we did everything asked in 11 and 12. On to 13. Here we have a piecewise function, 3 different pieces, and we're plotting them within different domains. When you graph these, it's important to know where these endpoints are. Also important to have some sense of what these equations look like, where the center of that equation, if it has a center, is. So you want to keep all this up front in your mind as you're working through these. So let's look at the first piece. We're going to graph -x² plus 3. Okay, so what do we know about that? We know it has a vertex at 0, 0. Well, the parent graph has a vertex at 0, 0, and it's been translated up 3 units. So if we first ignored our domain restriction, we'd be up at 0, 3. And then if we get a couple extra points, let's plug in a -3. Careful here, the equation has a negative, and x is also negative. So I'm putting what I'm plugging in parentheses. Follow order of operations. So -9 plus 3 is -6. So -3, -6 is a point that this is going through. Right there. And notice that's an endpoint. I plugged in -3. X is less than or greater than or equal to -3. That equal is telling me I want to color that point in. That's as far left as we're going to go. If you take a look at the domain, though, this thing is only going to end it when x is -1. Okay, so if I ignored that, this graph is looking something like, like that. But
we don't want the whole thing. We just want a piece of it. So I'm going to have to go back and erase that. And I will do that in a second. Before I do, let's see exactly what's going to happen at -1. So at g of -1, just going to carefully plug these in. We end up with 2. So -1, 2. Right there. Should it be closed or open though? It's just a less than sign, so we just want it open. So let's fix what we have here. Don't want all this stuff here. Just want a part of that. I want that actually to be open. And so just that piece. Okay, again, if we continued, it would max out here at our vertex, come back down, and keep going, but we don't want all of that. We just want a part of it. So we're done with our first piece. Just be careful. Second piece. I'm going to switch colors now. And I want to scoot this over a bit. Okay. So g of x equals 3 of x only for, again, a little piece. Okay. So first start by thinking, okay, what do we know about 3 to the power of x? It's exponential. It's a parent graph. It's got a horizontal asymptote. I'm going to erase this, so just bear with me here. It's got a horizontal asymptote along the x-axis. Goes through 0, 1. If you plug in the value 1, which we're going to need, we get 3 to the power of 1, which is 3. So 1, 3 is a point. If we were to plug in -1, which again we need, it's another endpoint, we get 3 to the power of -1, which is 1/3. And this one we're going to have to graph because that is an endpoint. So -1, 1/3, about right there. And typically, it goes through those points and gets closer and closer and closer to that horizontal asymptote if we didn't worry about restrictions. But we need to restrict this. It's not a function. If you do the vertical line test, maybe at -3, the way it's plotted here, I'm going to pass through 2 functions. I hit 2 points, not defined as a function that way. So we need to restrict this. And we only want a piece of what we drew, and that's our piece. We want closed circles at the endpoints because we have the less than or equal signs, both less than or equal signs between -1 and 1. Done with that piece. And then moving on to the last piece, 2x minus 4 for x greater than 1. So think about what do we know about 2x minus 4? That's a line. It's got a y-intercept at -4. Okay, again, this is going to be erased, so don't write this yet. And it's got a slope of 2. So up 2, right 1, up 2, right 1, and so on, up 2, right 1, if I can keep that pattern going, up 2, right 1, and there's our line. Sorry, it's a little crooked there, but that's y equals 2x minus 4. We only want a piece of that line though, and only when x is greater than 1. So x is 1 right here, and it's not equal at that point, so we want to open circle there, and we only want to graph to the right of that point, so I'm going to have to erase what's to the left of that point. And I'm going to put an arrow on the right hand side saying that we're just going to continue that on forever to the right. We don't put an arrow on the far left because it's not continued as far left as we want. And so there's our piecewise function. It looks a bit weird, but there it is. Find the domain. Okay. So the furthest to the left, the furthest is negative 3, and that's included at negative 3. We get a solid point. Furthest to the right is, well, it's going to go as far right as we want, infinity. And before we feel good about this interval, let's just make sure there's no gaps in between, because if there are, we're going to have to split up this interval. There's a break in the graph at negative 1, but negative 1 is represented because there's a solid blue dot there. There's also a break in the graph or discontinuity at 1, but again, there's a solid blue point represented, and so there's no gaps in our domain. Okay. Find the range. So the lowest point is at negative 1, 2, 3, 4, 5, 6. Negative 6 is the lowest, and it's included. The highest point, well, this green arrow is pointed up as high as we want to go, so up to infinity. But again, let's just make sure there's no gaps in between as we go through. You know, there's an open circle at negative 2, but if you move to the left, the black curve is represented at that point, so we're okay. And once from that point, the green just takes over. Everything in the range that we've from negative 6 to infinity is covered, so there's no gaps. And we finished 13. 14. Sketch the graph of f of x equals 2/3 times x minus 4 squared. If x is less than 2, using at least 3 lattice points. Okay, so what kind of function is this? This is a parabola. This is a quadratic function. It's going to give us a graph of a parabola. It's not the parent graph. We know the parent graph has a vertex or y-intercept at 0, 0. This has been translated to the right 4 units. So from 0, 0, I'm going to move right 1, 2, 3, 4. And so we're represented at 4. I'm going to move to the right one more. I'm going to plug in x equals 5 to get a second point. We want at least 3. And as I work through this, we end up with 2/3. That is a point 5, 2/3. At 5, I'm going to go up just a little bit, but that's not a lattice point. We can only work with integer values for it to be a lattice point. So we need to work a little more carefully here. Instead of having a 1 squared, because the denominator is 3, I'd love to have a 3 squared. So what minus 4 is going to give us 3? 7. So let's plug in 7 into the function. So we end up with 2/3 times 9. When you multiply a fraction times an integer, you can view that integer as a fraction as well. You multiply numerator with numerator, denominator with denominator, you get 18/3, which reduces to 6. So 7/6 is a lattice point. So let's plot that. 4, 5, 6, 7, up 1, 2, 3, 4, 5, 6. And that's the right side of our graph. We're also going to go, because of symmetry, we automatically get that third lattice point at 1, 6. And there it is. Our domain, this reaches as far left and as far right as we'd like. We can say all real numbers. For a range, the lowest point is 0, it's included, and it goes as high as we want. Or we can say all y values greater than or equal to 0. (15) We have an equation of a line, but it's under a certain restriction. We're only going to graph it from -2 to +2. To graph a line, you only need 2 points, and because we have to know the 2 endpoints, let's find those 2 points. So let's plug in -2 for x. (1/2) times -2, that's going to give us +1 plus 4, end up with 5. So -2, 5 is our first point. And then our next point, I'm going to plug in the second endpoint. So I plugged in -2, now I'm going to plug in +2. F of +2 (1/2) times 2 is -1. (1 plus 4 is 3. So 2, 3. Have our 2 points. And careful here, those are the endpoints. So we're only connecting what's in between them. You know, if we asked to graph the whole line, we'd extend past those points, put an arrow on each end, but this is restricted. We have 2 points, that's all we need to graph it, but it says we need at least 3 lattice points. We can kind of see, just from our graph, another lattice point at 0, 4. And we can confirm that. You look at the equation, if you plug a 0 in for x, you're going to lose that (1/2 x), and we're left with 4. And so now we have our third lattice point. 16. Give values for a, b, and c for the equation f of x equals a times x plus b squared plus c, so that the vertex is at -2, 4, and opens down. So we have a little bit of freedom here, but we have to make sure it meets our criteria. 2 criteria, it's got to be in this form. That's the third, I guess. It's got to have a vertex at -2, 4, and it's got to open down. So in order for it to open down, we need a to be negative. For our vertex to go through -2, 4, we're going to have a translation from the parent graph, left 2 units, up 4 units. Okay, so a is negative, we get to pick any negative number we want. Let's pick -5. And put this together. So f of x equals a, so -5, parentheses x. Now it's 2 units to the left, so +2 squared, don't forget squared, up 4 units, so +4. So give values a, b, and c for this equation. So a we said is -5. B, well, in the form we have x plus b, so b would be 2. If it said x minus b, we got to be careful there, but we'd have to put -2 to get a +2. Double negative gives us a positive. But we have an x plus 2, so we're just going to grab our 2. And c we want to be +4. So if we plug those into that equation, we end up with what we have here, and that gives us a vertex at -2, 4, and opens down. 17. John's at a carnival where it costs $10 for admission, and each ride costs $2 to ride. P of R represents the total cost for the carnival in dollars as a function of R, where R is the number of rides John goes on, and R is between 0 and 5. Sketch the graph P of R. Okay, so P is our price, R is how many rides you're going on. So at 0 rides, you'd end up paying $10. We need to decide on our scale here. I'm going to go by 2s. So 2, 4, 6, 8, 10. And so if John gets into the park and doesn't go on any rides, he's going to pay $10. But it says he's gonna have at least well, we want to graph this between 0 and 5. So we're starting at 0. So open circle there. And here's 1, 2, 3, 4, and 5 rides. So if he doesn't go on any rides, he's just going to pay $10. Okay. But say he wants to go on one ride, he's got to pay an additional $2. So now he's paid $12. Close circle. So that first part from 0 to 1 is just saying, well, between 0 and 1, there's a flat rate of 10. It's not increasing. I don't want to draw, and I'll do this. I don't want to draw this like a slant line from those 2 points because you're not paying anything between $10 and $12. There's a jump at one ride from $10 to $12. So I have to draw these, in a sense, steps or horizontal lines to represent this. So again, between 0 and 2, you're paying only $12. But once you get to the 2, you're paying an additional $2. And then it's repeated. Jumps another 2. This is at 12. It's at 14. This is up here at 16. Jumps again. Up at 18. It just keeps repeating. And then at 5, it jumps again. Right there. Okay. So this is the kind of graph, and we just have a point at 5. We're stopping at 5, but we want it to be equal to 5. And so this is what this looks like. So we have 1, 2, 3, 4, 5, 6 individual pieces, and so here's what our piecewise function will look like. P of R is equal to $10. And between 0 and 1. In context, this isn't really going to happen, right? You can't be between 0 and 1 ride. So there's an argument we can actually not even graph this part or throw this piece out. I'm going to leave it like this, but just think about what this is meaning. You have to be on more than 0 rides but less than 1 ride, not going to happen. So we're really not going to even pay $10. Okay. The next part, we're going to pay $12 for r being equal to 1 or less than 2. Again, we have a similar thing here. It's kind of a weird thing with the domain. In this situation, our domain really is not continuous. It's jumping from 1 to 2 to 3 to 4 to 5. It's more discrete. We're graphing it as if it's continuous. So it's not a good problem in that sense, but let's bear with me. In terms of graphing or representing what's graphed there, that's the equation. And then 14 for 2 less than or equal to r less than 3. 16 for 3 less than or equal to r less than 4. 18 4 less than or equal to r less than 5. And 20 is just a point. So that's for r equals 5. So we can view this step function as separate pieces there. Now, what value of r is the function not continuous? So we have this discontinuity at every integer value, and we're only working between 0 and 5. We're not including 0. So we have a discontinuity at r equals 1, 2, 3, 4, and 5. Those are where the jumps are. C says write the equation for this piecewise function. We did right there. And that's it. Good luck on the test.